Hello friends, so today we are going to solve 3 questions, and these 3 questions are from electrostatics. So 1 second. So in the first question, it states that consider a large flat horizontal sheet with a thickness x and volume charge density rho. This sheet is tangent to a sphere with radius r and volume charge density rho naught as shown in the figure. Let A be the point of the tangency and let B be the point opposite to A on the top side of the sheet. Show that the net upward electric field from the sphere plus the sheet at B is larger than A if rho is 2/3 of rho naught. Assume x is much smaller than r. So basic figure is already given to us. So we have a sphere whose charge density is given as rho naught, radius is r, and on this there is a sheet of thickness x. A is the point of tangency and B is the point that is just opposite to it, and rho is the density, charge density of volume charge density of this sheet. And we have to find out the electric field at B will be greater than electric field at A under the condition that rho is greater than 2/3 of rho naught. So that's a basic question. And so first of all, let's start with the sheet. And so we can say that field of the sheet and the sheet is given to us as a thickness of x, okay. And we are given the sheet is having a x as its thickness and rho is its volume charge density. The volume charge density. Okay. Therefore, we can write that so you can say that effective surface charge density and let us suppose that you have a sigma, then sigma will be equal to rho times x. Okay. And because this is given is like a thin infinite sheet, therefore we can say that electric field of the sheet will be equal to this. We can write as sigma upon 2 epsilon naught. Sigma we just found out. So this is a rho x upon 2 epsilon naught. And in this case, we have to remember that the field of the sheet will be pointing upward, and for the below the sheet, it will be pointing downward. So we can say that of the sheet, we can say that our field points upward, and below the sheet the field points downward. Field points downward. Now let's find out the electric field because of the sphere. So you can see that our field of the sphere. So for that, let us first of all find out what will be the charge on the sphere. So you can see that our charge on the sphere, let us suppose it is given as Q, then Q will be equal to its volume and multiply by the volume charge density that is given as rho naught. Therefore, we can write that electric field at a distance r from the sphere. So we can see our field at a distance r, we can, or let us call this as outside the sphere. Outside the sphere. And for that, we can write the electric field of our sphere at the distance r will be equal to 1 upon 4 pi epsilon naught charge on the sphere and the square of the distance. And let's now find out, based on our this r distance. Now this r can be divided into two parts. In the first part with respect to point B, and the second part will be with respect to point A. So with respect to point B, this r distance will be equal to r plus x, and with respect to point A, this r will be equal to capital R, because A is nothing but the point of tangent, okay, and B is just opposite to it at a distance x from A. Therefore, we can say field at point B and for that our distance r will be equal to capital R plus x. Therefore, we can write, now we have the field due to sheet is our rho x 2 epsilon naught, okay, and above the sheet it will be upward and below the sheet it will be in the downward direction. So now we find out the field at point B, that will be the field due to this sphere and the field due to the sheet. Therefore, we can write the total upward field. Total upward field, let us call this as our EB, will be equal to 1 upon 4 pi epsilon naught, and we can substitute value of our Q, that is our 4 by 3 pi r cube times rho naught divided by r plus x, because now small r is equal to r plus x, okay, and plus rho x and 2 epsilon naught, because field due to the sphere as well as because of the sheet will be upward in both cases. So it will be just addition, okay, because this electric field due to sphere is also in upward direction, and field above the sheet, which is nothing but our point B, is also in upward direction. Okay, so the both are going to algebraically add. Whereas for our field at point B, field at point A, now in this case our R is equal to capital R. Therefore, we can say that the total field let us call this as EA will be equal to 1 upon 4 pi epsilon naught, and this is over 4 by 3 pi r cube times rho naught, and this comes as r square. And now in this case it will be minus, because in the field it is in the downward direction. So this comes as a rho x upon 2 epsilon naught. Okay, because field in the sphere is still in upward direction, and below the sheet, which is nothing but our point A, is in the downward direction. So therefore we get the field at point A is subtractive. Now it is asked in the question that our electric field at B will be greater than electric field at A. Okay, so we have to find out that condition and match with the answer. So we simply substitute the formulas, and that is our 4 by 3 pi r cube times rho naught divided by 4 pi epsilon naught r plus x whole square plus rho x 2 epsilon naught should be greater than, and here we have about 4 by 3 pi r cube rho naught r square, and this is about 4 pi epsilon naught minus rho x upon 2 epsilon naught. And this is quite easy to solve. Okay. And we can rearrange it, and that rearrangement is going to give us an equation that rho x should be greater than our r times rho naught upon 3, and this becomes 1 minus 1 upon x plus r whole square. Now we are going to use the approximation that is given in the question. It says that our x is very much less than our r. Okay. For that we are going to use this expression. So let us assume that this is x upon r is approximate, let me write it other way. So we assume that our term is epsilon, that is x upon r, which is very much less than 1. So therefore we can write this equation as 1 plus epsilon whole square, and this will be approximately equal to 1 minus 2 epsilon. Okay. And so we take this entire bracket and we get this as 1 minus 1 upon 1 plus x r whole square. This will be approximately equal to 2x upon r. Okay. And so we substitute back into the equation, and we get this as our rho x should be greater than r rho naught. This is 3, and it becomes 2x upon r. So it means our rho should be greater than 2 by 3 times rho naught. That was the condition which was asked in the question. Okay. So we got the solution of our first question, and now we come to the second question. In this second question, it states that it's quite simple actually. We have done this many times, okay, but the question is asked a little bit different way in this particular question, but the solution is quite easy. We have done this regularly in our board examination also, and during the preparation of the JEE. It is quite simple question. Okay, but let us focus on the statement that is given in the question. Consider the electric field at a point on the surface of A. So there are 3 surfaces: a sphere of radius r, a cylinder with radius r whose length is infinite, and a slab with thickness 2r whose other 2 dimensions are infinite. All of the objects have same volume charge density rho. Compare the fields in these 3 cases and explain physically why the sizes take the order they do. So this is nothing but a comparison thereof electric field. And so they have this everything is same. They have the same charge density, only this you can see slab is having thickness 2r and the sphere and the cylinder is having the same radius. And so we are going to use the Gauss law in each of the cases. So let us start with our first case, and that is our solid sphere. And solid sphere, it is given that it is having a radius, and that radius is our r. So based on this, we can write that the total charge, which is our q, and that total charge will be equal to our 4/3. This will be our 4/3 pi r cube multiplied by the charge density. And the electric field at the surface we can easily find out. So you can say our field at the surface, and let us call this as E sphere at a distance r, which is that surface, will be equal to 1 upon 4 pi epsilon naught q upon r square, and we substitute value of q. So this gives us that electric field because of the sphere at the surface r will be equal to 1 upon 4 pi epsilon naught, and q is our 4/3 pi r cube rho 1 upon r square. And this pi 4, and this cube goes by the square, so we are left with only rho r, and we have this 3 epsilon naught. Okay, so this is electric field at the surface. Now we come to our infinite solid cylinder. Infinite solid cylinder, and this radius is also given to us as r. And so let us consider a Gaussian surface of radius r and length l. So we consider a Gaussian surface which is having the same radius, that is our r, but we have considered this as length as our l. So therefore we can find out the charge enclosed and this charge enclosed will be over q, and that will be equal to our pi r square l, that is a volume, and multiplied by charge density. And we can write it by Gauss law. You can say that by Gauss law, electric field for a closed surface, if you integrate it, that will be coming as 2 pi r times l, which will be equal to, and this charge is given, we found as our q upon epsilon naught, and this comes as our pi r square l rho times epsilon naught. So here also we have our pi r goes by the square, length and length cancels out, therefore we get that of electric field because of the infinite cylinder is equal to rho r upon 2 epsilon naught. Okay. And this, okay, let me come to that point later on. Now we come at our third part, that is infinite slab. Infinite slab, and its thickness is given as 2r. So once again we can use our Gaussian law, and we can say the charge enclosed will be our Q is equal to rho 2r times A. And now we can write from Gauss law we have this, our 2EA will be equal to our charge enclosed upon epsilon naught. This comes as our 2RA rho upon epsilon naught. Here 2 cancel with 2, area goes by area. Therefore we get that our electric field because of our slab is equal to rho r upon epsilon naught. These are the standards, you can say, formulas. If you know the formulas, you can also directly solve it. And we have to take care of the sheet only, because here the thickness is given as 2r. So we found out that our electric field due to sphere is our rho r upon 3 epsilon naught. Electric field due to our cylinder is our rho r upon 2 epsilon naught, and electric field due to infinite slab is our rho r upon epsilon naught. And if you look closely to the denominator, we can clearly see this is our 3, 2, and here it is 1. And if you arrange this electric field, so we are going to get the electric field of the slab will be greater than our electric field because of our cylinder is greater than electric field because of our sphere. And we can also say that our the sphere is having the weakest electric field because charge is distributed all the direction, okay, and fields spread out basically in 3 dimensions, so which leads geometric dilution of the electric field. Whereas the cylinder, the charge extends infinitely in only one direction, and field lines are, you can say, out in 2 dimensions. So there is a dilution, but as compared to sphere, the dilution is much more lesser. And slab is, you can say, the field has in 2 directions, and the charge extends in 2 directions, whereas the field spreads in only 1 dimension. Okay? So there is a minimum geometric weakening. Okay? This is just, but important point is that they extend with the ratio of 3, 2, and 1. The rest of the parameters same, rho r epsilon naught and rho r epsilon naught. So this was quite simple, but asked in the different, you can say, point. Now we come to our third question. In the third question, it states that a hemisphere shell has a radius r and uniform surface charge density sigma, as in figure. Find the electric field at a point on the symmetry axis at position z relative to the center for any value of z from minus infinity to plus infinity. Okay. So this is our basic question. And in this case, we are going to, because z-axis is normally given to us, it is sphere of radius r. And for that, let us consider a ring. So this is our sphere, and suppose this is our center, and we consider a ring in this that will be something like this, and this is at a radius r, and we are supposed to deal with in the z direction. So this is a z axis, and let us suppose this is a point somewhere on this axis, and this point is at a distance of small r, and let us assume that this angle is our theta and this distance is our z. So because then we are going to add this ring systematically with respect to the angle theta. Okay, so if we add on these rings, we are going to get this as a hemisphere. So we start with our consider a thin ring, okay, and this ring is having a ring width and that ring width is, let us suppose, d theta. Okay. Therefore we can write the radius of the ring, because this is nothing but a 90 degree, okay, and we can find out the radius of the ring. Therefore we can say that ring width is d theta, and okay. So therefore we can say the radius of ring, let us suppose that is our a, and this a will be equal to our r sine of theta. Okay, so this is our radius of the ring. And from here we can easily find out the area of the ring. Area of the ring, and let us suppose that is our dA, and dA will be equal to our 2 pi, and we have our r sine of theta, and multiply by our r d theta. And now from here we can find out the charge on the ring. Charge on the ring, and let us suppose that charge is our dq, then this dq will be our charge density and multiply by the area. And so we can write that our charge dq will be equal to sigma, and we can write this as our 2 pi our r square sine of theta times d theta. Okay, so we found out the charge on the ring, and based on the charge on the ring we can find out what will be the field at the point, which point is our P. Let's find out the field at point P, and for that we can easily use our cosine law. So we can say that field on the point P, okay, and for that we can use our cosine law, and that cosine law is going to give us r is equal to r square plus z square minus 2r z cos of theta and its square root. So we found out value of r, and now we are going to use this value of r later on also. And first of all, let's find out what will be the various components that is going to affect the field at point P. And we have to remember that we have taken a point. Let us suppose this point is on the right side is of Q, that the corresponding point on the left side is, let us suppose, of Q prime. Similarly, in this, from the figure we can say this Q and Q prime are symmetric. Okay. Similarly, there will be a n number of points which are also symmetric with each other. Okay. So because of this, what is going to happen, their horizontal components are going to cancel out, and only component that will be left will be the vertical component. Okay. Or in simpler words, we can say that every charge element on the ring has a partner on its opposite side. So Q is having a partner of Q prime on the opposite side. So because of this, the horizontal component of this Q will be cancelled out by the horizontal component of this Q prime with respect to its partner. So only thing that is left will be the vertical component, or we can say axial component. In this case, that is nothing but our z direction. So this point is important, and there is no need to, you can say, drive all these things, because we know that whenever there is a pairwise, we are going to get their horizontal component in this particular case will be cancelled out. And therefore we can say that every charge element on the ring has a partner on the opposite side. On the opposite side. Therefore, we can say that their horizontal component horizontal components cancel pairwise. So it means the horizontal component of Q will be cancelled out by the horizontal component of Q prime. And suppose there is another variable, that is our element is A, then its horizontal component will be cancelled out by the A prime. So we can say that only the axial, which in this case is our z direction, components add. So this is a, you can say, important conclusion which we can draw from here. And so because of this, okay, so in this case, let me redraw this figure again, okay, only with respect over this distance, is nothing else. Okay, so we consider, and let us consider this point is our C. Okay. So we have our C, and then we have our Q, and this C and Q is giving us our R. And there is a point P, and this P is our small r, and this angle is our theta. And if we join our this vertical in this direction, and let us suppose this angle is our phi. So it means from this, now let's find out what will be our field direction, or we can say geometry of the field direction. geometry of field direction. And from this figure which I have drawn, we can clearly see that field from each charge element points along the line joining to the field point. And so in the shorter terms, we can write that we assume that the field is making a phi angle below the horizontal. So let's write it out. We can say the field is making a angle phi below the horizontal. Therefore, we can, because the direction is nothing but our z direction, so we are going to call this as a z component. Okay. Therefore, we can say that the z component we can write this as, because we have taken this small element, so this is a small element at q, and that will be equal to our Ez is equal to E, and this comes as minus sine of theta. Sorry, not theta but phi, because angle is over phi. And we have to remember, in the question it is only asked that what will be the field in z direction or z axis, okay, at point P specifically. So we are not bothered about at any point, we are only interested in the electric field which will be along our z axis. Okay. And this minus is nothing but it's point out the direction. So it will be going as this will be our sine of phi in the downward direction. Okay. So this will be our sine of phi. Okay. And with respect to our electric field, and this will be in the downward direction. Upward is a positive, so downward will be obviously the negative sign. Okay. And we can find out, let us, this is C and this is our C prime. So we can easily find out the distance. Okay. And we can say that our PC was our Z, okay. And therefore we can easily find out this PC prime. Okay. We can say that our PC prime will be equal to r cos of theta minus z. Okay. Because z is our, this is our r, this is our theta, so this is our r cos of theta and this is our z. So we get r cos of theta minus z will be our PC prime. And therefore we can from here write that our sine of phi will be equal to our r cos of theta minus z upon small r. Okay. In this triangle, so this is our 90 degree, so PC prime Q is our, this is going to be the sine of phi. And let's find out the field from one ring. This is a small element Ez, okay, and so you can say that our field from one ring and we can say that our dE will be equal to 1 upon 4 pi epsilon naught. Charge is our dq and distance is our r, that is our r square. So this is the field from one ring at point P. Okay, so everything we are going to calculate is with respect to point P, which is lying on our z axis. So we are only interested in z axis, nothing else. And so therefore we can say that this field in our z direction will be equal to, this will be minus, and we get this as 1 upon 4 pi epsilon naught, and this is a dq upon r square, and multiplied by our, that is our sine of phi, which is our r cos of theta minus z upon r square. So this is our electric field in the z direction. Now we substitute value of our dq, so we get this as our dez, electric field in our z direction will be equal to minus, and we substitute dq, and dq is our, so we substitute this value, sigma 2 pi r square sine theta, okay, d theta. So we get this as sigma 2 pi r square sine theta d theta, and rest is our same 2 pi epsilon naught, and this gives us r cos of theta minus z, and r we already calculated, we need a r square, so we just calculated our r according to our cosine law. So this will be r plus r square plus z square, so this is our z, so this is our r square plus z square minus 2r z cos of theta, and this will be our r square, and this will be r square, so this will be r4. Okay. Sorry, 1 second, this is r not square, so this will be r cube, so we are going to get this as 3 by 2. Now for a hemisphere we are going to integrate it from 0 to pi by 2. So you can say that for hemisphere our theta is 0 to pi by 2, and now it is quite simple. Okay, it is only left with integration, so we get electric field along z direction that is our E of z will be equal to minus, and this will be coming as this pi cancels out, and this 4 goes by 2, and this will be coming as our r cube, so this will be sigma r cube and 2 epsilon naught integration 0 to pi by 2, and we are left with our sine theta, and we have our r cos of theta minus z, and in the denominator we are going to get this as our r square plus z square minus 2r z cos of theta and our 3 by 2. Okay. So now this is a simple, not a simple, but it will take a little bit of effort, and for that we are going to assume that our denominator is equal to our u. Okay. And that is going to help us to sort it out. Okay. So we get this as our we can say that our u is equal to r square plus z square minus 2r z cos of theta. Okay. It will be a lengthy process. I'm going to still, you can say, put the limits. and we are going to get this as our E of z will be equal to sigma r square 2 epsilon naught, and we get this as our r minus z cos of theta, and this will be our z square r square plus z square minus 2 r z cos of theta, and this is our 1 by 2 0 to pi by 2. Okay, so we can, the upper limit is our pi by 2, so cos theta will be equal to 0, and lower limit is 0, so cos theta will be equal to 1. Okay, so let us sort it out. So we can say that our theta is equal to pi by 2, so we get our cos of theta will be equal to 0. So it means this term will be equal to 0, and this term will be also equal to 0. So this will be giving us r upon, and okay, so from here we can write this will be equal to r square plus z square and square root, and so we can write it, we are going to get this as our r upon z square square root of r square plus z square. Okay, and now we come to our theta is equal to 0, so we get our cos of theta will be equal to 1, and so cos theta is equal to 1, so this will be r square plus z square minus 2rz and its square root. Okay, so we can say we get from here that r minus z whole square and its square root, or we can say this will be r minus z and in terms of our modulus. Okay, therefore it will be giving us our from our r minus z upon r minus z, and this will be our z square, and here we get our r minus z. So now we can combine them, and we get that electric field will be equal to, this is sigma r square 2 epsilon naught, and z square is common to both, and this comes as our r upon r square plus z square square root minus r minus z upon modulus of r minus z. Okay. Now this will be valid except for z is equal to 0. So it is valid for all the values except that our z cannot be equal to 0. And everything will be dependent upon this sign, we can say will be dependent upon our this factor. Okay. And we can divide this, so we can say that we are interested in the term that is our r minus z upon r minus z, and this will be our giving us our plus 1, under the condition that our z is less than r, and this will be giving us -1 if our z is greater than our r. So this is quite simple arithmetic now. So therefore we are going to get two values of this depending upon value of our z. Okay, so we have two values of z in comparison to our r. Therefore we can say that for our z is less than our r, so we are going to get that our E of z will be equal to sigma r square 2 epsilon naught z square, and this will be equal to 1 upon 1 plus z square upon r square square root -1. And similarly we can write for z greater than r. So we get this as our E of z is equal to, this is our sigma r square, and we have 2 epsilon naught z square. This will be same except here will be a positive sign, z square upon r square square root. Now it will be +1. So this is our electric field depending upon whether the point z is greater than r or less than r, but the point cannot be equal to 0. And so this is the basic our today's 3 questions. Okay, and in these 3 questions, the second one was, you can see we have done it multiple times, but minor difference was how the question was rephrased. Okay, because the phrasing of the question is very important. And similarly we dealt with our question number 1 and question number 3 because they were a little bit, you can say, asked in the entirely different way. So this completes all the 3 questions. Thank you.